Hi everyone! So this is the fifth video of the Heap series, and in this video we are going to talk about Heap implementation. So in the previous videos that we've done, we actually looked at simply what heaps were, complete binary trees, how to do insertion, how to do removal. But what we haven't done is we haven't actually talked about how do we implement this thing. What is the code for this particular data structure? How will we do it? What's the underlying data structure and things like that? How do we make sure that these operations that we want to do are going to be fast? Because we've actually been taking a whole bunch of things for granted as to how we would actually accomplish things. So, uh, so in this video, we're going to actually sort of break open that mystery. How do we do this, right? So here is sort of the biggest surprise about a heap implementation. The first thing you should know about a heap implementation is that heaps are implemented using just an array. Which is sort of weird because they don't look like arrays to you, right? Like it's got circles and sticks. It doesn't look like an array. We always draw those with boxes, right? And that part is absolutely true. But they are actually implemented as arrays. Heaps are implemented using arrays. Okay, it's actually what allows them to be implemented quickly. It's not just a data structure um, it's actually it's actually necessary to do it as an array for a binary heap to be fast and efficient and all the other stuff. So how do we do this? How do we use an array, which we normally think of as flat and like a strip of numbers, right? Like, you know, there's the first number, there's the second number. How do we turn that into this? And the idea is actually quite simple. So here is, we have a min heap in my picture right here, okay? So we've got one as the root and values ordered in a min heap manner. How would we actually implement this heap using an array? So let's start with that, okay? So here's our array, and I'm gonna put in the index numbers because they're important to the discussion, okay? Now let's talk about what we do with this. So first of all, um, one, the root of a heap is stored at array sub 0. Now I know the textbook doesn't. Some textbooks say don't do it at 0 because you can skip an operation if you like one like operator like literally a subtraction. If you do it without, if you use 1 as the starting index, don't do that. That's silly. It actually just, why, right? So don't do it. Okay. For us, very simple. Root is at 0. Okay. Um, so with this in mind, with root being at 0, what it means is that this heap in memory is actually stored in this manner. 1 is actually placed in the 0 element because it's the root of the heap, right? Now, what is next? Well, the way that we define relationships is actually based on mathematics involving the index. Okay, so for any given node where the index, where the data is stored at index IDX, the left child is at IDX times 2 plus 1. The right child is at IDX times 2 plus 2. The parent for non-root nodes, so every node except the root has a parent, okay? So for anything that's not a root, it is IDX minus 1, and then take the whole thing and divide it by 2. Okay, so that's the math. Okay, now we're going to see this in action in a moment, but this is actually the mathematics of how do you figure out where to put your left and right child? Where should these guys go? Okay, so let's start with that. Now, root node, so let's use this as an example. So our root node over here is at index 0, right? So the left child of the root, where would that be? Well, according to this, it's supposed to be at index of the root plus times 2 plus 1, right? So it's idx times 2 plus 1 is the formula. In this case, the root node is at index 0 times 2 plus 1. The right child of the root is at 0 times 2 plus 2, okay? Because again, the root is at element 0. So its left child is at 0 times 2 plus 1, and its right child is at 0 times 2 plus 2. So in this case, this number here adds up to 1. This one adds up to 2, okay? Now, where's the parent of the root? Well, there's no parent for root, okay? So this formula only applies to non-root nodes, so no parent, okay? But what this means is that 8 is actually placed right there. 10, which is one's right child, is placed right there. Now, let's take a look at left of 8, of node with 8, okay? So where would that node be? So left child of the node with 8, where's that? 8 is stored in element 1, right? So 1 times 2 plus 1, that would be 2 plus 1, which is 3. The right child of the node with 8 is equal to 2, not 2, 8 is at 1. So 1 times 2 plus 2, which is 2 plus 2, which is 4. Okay, so 8's left child, 9, is stored at 3. 8's right child, 12, is stored at 4. Huh. So in other words, if I actually were to write down the indexes of all the nodes, 1 is stored at index 0, 8 is stored at index 1, 10 is stored at index 2. My handwriting is kind of horrible there. 9 is stored at index 3, and 12 is stored at index 4. And so what we have is we actually can see sort of a pattern. Now, where do you think 10's left child would be? What's the math, right? So if we do the math for 10, 10 has an index of 2, right? So what is the left of 10? Where do you think, what number do you think it'll come up with, right? So left of the node with 10 is going to be equal to, well, it's 2 times 2 plus 1, which is equal to 4 plus 1, which is 5. So this node, which is over here, which we don't really have, that one will end up at index 5. Its right child would be 2 times 2 plus 2. So if we actually had a right child, it would be at index 6. And, oops, sorry. Just realized I've been cutting off. Now, the node for 9, left of 9, 9 is 3. 3 times 2 is 6, plus 1 would be 7. So the left-hand child of 9, this would be at index 7. The right-hand child of 9 would be at index 8. And so the really neat part about this is that we actually simply can think about our indexing in this manner. You just simply go across 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 15, and then continuing from there. Sorry, I'm probably miscounting. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 15 is the next level after that. So all the way up to 14 and so on. So this is how this works. Now, the parent is simply going backwards. So let's make sure that our math works out, right? So let's take in node 12. Where is the parent of 12? So according to the formula, right, 12 is at index 4. So parent of 12 is at 4 minus 1 divided by 2. So 4 minus 1 is equal to 3. 3 divided by 2 is going to be 1.5. Now, remember that this is integer math. And whenever you do integer math, you ignore the decimal places, right? So even though this number comes out to 1.5, we chop off the decimal places and we end up at 1, which is why this is at 1, okay? So index 4, okay, ends up having a parent of 1. Okay, so this is basically the way to implement a binary heap. You simply use an array, which is kind of neat. Okay, so that's pretty much the basics of it. Okay, now there are some really big advantages before we go on to the next video of doing it this way. So remember when we did insertions, what we had to do was we had to find the bottom rightmost node, right? And when we did removals, we also had to find the one at the bottom rightmost that is exists, right? So if you think about how you do an insertion, what do you have to do? So what if we had to try to do an insertion into this heap that we have over here? So we started off with this heap, okay? This was 1, 8, 10, 9, and 12, right? So here is our array. And if we wanted to do an insertion, 0, 1, 2, 3, 4, and then 5, um, when we are looking at something like this and we're trying to do an insertion, what is the algorithm? So let's say that I wanted to do insert the number 6. Okay, simple. Now, remember that when you do this, the first thing you do is you create a node so that the tree stays complete, right? Now, that means that I have to somehow figure out where the tree ends. Okay, like where is this? Like in the picture, it's easy to tell. Oh, it's the left child of 10. That's easy to tell. But remember that we don't store our tree like this. Our computers can't visually see the tree. So how can it tell where the left child of 10 is supposed to be? Or if that's even the node that you want, right? Because remember, this tree could get actually really, really big. How does it know where the bottom is, right? Like where does it end? Whether it's the left child or right child, especially when all you have is like the root, right? So if we actually use a linked data structure for this, finding that bottom rightmost node is actually not trivial. You'd probably have to track it as you go. And even then it's sort of kind of like, ooh, this might not be the easiest thing to do. So um, instead of doing that, the array version, though, if we do this with an array, it's actually really, really simple. We actually can tell how big this thing is, right? So 0, 1, 2, 3, 4, right? So this particular heap has 5 things in it. So currently our numbers, as we've done in the previous, 1, 8, 10, 9, 12. The interesting part is that when I want to add something, to the heap, the node that I have to add corresponds to the end of my array. So as long as I track how many things are in here, adding something new involves putting a new value initially. We think of this as the open, the empty node. This is where we're going to begin, right? Also easy to tell when we need to grow our array. Okay, now because this tree is complete, we will never have any gaps in our arrays, because in order for there to be a gap, we would actually have to, it would imply that a node is missing, right, somewhere in the middle. So like if I was missing the 8 node, or sorry, the 10 node, for example, then there would be a gap, right? So I would have an opening right here. But I can't do that with a complete binary tree. I actually have to fill it in top to bottom, left to right. And so because of that, there won't be any like empty spots somewhere in the array. As long as I keep track of how many I have, I know exactly where the bottom rightmost node will ever be. So that's really, really handy, really easy to do because I just know, oh, 5 things. So then when I add something new, we try to put it into array 5 first. Then what do? We say, okay, uh, can I put 6 here by, then I check its parent. How do I find the parent of 5? Well, the parent of 5 is 5 minus 1 divided by 2. That's just math. The computer can do that very quickly, right? Which is equal to 4 divided by 2, which is equal to 2. And so I check array 2, and the 10 over here, well, okay, it's bigger, so that's not good. So what do? We move the 10 into the empty spot, and we consider putting 6 here, right? So in this particular diagram, the 10 is moved down the tree, and now we say, can I put the 6 where the 10 was? Again, check the parent, right? So 2 minus 1 divided by 2 gives you 1/2, which is actually equal to 0 because um, half is 0.5. Chop off the decimal parts, you only had 0 left, so that's why it is. And now we put the number in. 6 goes here because it doesn't break any rules, so we're good. So this is effectively how you would implement the tree. You simply use a formula for parent, a formula for left, formula for right. You can write this as a function, right? Like left child, given an index, where's my left child, right? Given an index, where's my right child? And so on. Like you can code this fairly easily. And that's pretty much how you implement a heap. You don't actually use link structures, okay? Now, other trees are not implemented this way because other trees are not complete. Whenever you start opening up, having a possibility of having no node somewhere, what will end up happening is you will actually start having not only the missing node, as an empty spot in your array, but all of its possible children as your tree gets bigger and bigger and bigger. So if let's say that I don't have this node right here for the 10, and not only will I not have the 10, I won't have its children or its grandchildren or its great grandchildren, right? So you would start getting these like one little gap near the beginning, and then you would get 2 later on, and then 4, and then 8, and so on. So you end up with these like arrays that have a lot of empty spots in them, um, and that could be problematic as your tree fills up. So this implementation is usually typically used for heaps because it's got this nice completeness that you have to maintain, but it's not usually used for like regular binary search trees just because of all of these like holes and so on, and it necessarily doesn't necessarily help. So there's reasons to do it. There's reasons not to do it as well. Okay, but with a heap, it's kind of handy because I can tell exactly where the bottom rightmost node is. If I were to do a removal, by the way, this also really helps because remember, what do we empty out? We empty out the node that's we empty out the root, but we erase the node at the bottom right, right? So if we had a heap that was, oops, wrong tool. If we had a heap, let's say that this was our heap, and we wanted to do a single delete min operation, get rid of the node 1. What do? Well, what we would do is we would first start by saying, okay, we're going to erase. So remember, this is our array. 1, 6, no, sorry, one. It's actually 1, 8, 6, 9, 12, 10. Excuse me. So how do we erase the 10? Okay, what we do is, how do we, oh, sorry, how do we do a delete min? So we erase the one because the one is the one that has to go away, but we have to get rid of the node that contains the number 10 in it. So now when we think about it, we say, okay, that just means that's the shape of the tree, and we have to find a new home for 10. So in our array, we do the same thing. We basically say, okay, take the 10 here, and we're just going to try to put it into the spot right here. Okay, is it okay here? And the answer is, of course, no. What do we do? Well, what we do is we say, who's the smaller child? Who's the higher priority child? That would be the 6. Take the 6, move it into the root. Can I put the 10 there? Well, this node has no children, right? So of course, sure, you can put it in there. And now we're done. So the operations that we do, the operations that we want to do, is easy to do using an array implementation of this particular tree. So that's why we do it this way. Okay, it's actually easier. The operations are faster. Okay? And that's pretty much everything for this video. Okay, thank you. In the next video, we're going to talk about how to create a heap in place with an array. Okay, thank you.